Hello! In the next couple segments, we'll be looking at components of a photovoltaic circuit. By the end of these lessons, you should be able to relate semiconductor properties to electricity generation in photovoltaics. You should be able to explain how a photovoltaic cell functions within a DC circuit, and you should be able to measure current and voltage in a photovoltaic module. Finally, you should also be able to define and evaluate the characteristics of an IV curve. Let's begin by looking back to a basic circuit where there's a power source, a load, and the conductors. Let's drill down a little bit closer to see how the photovoltaic device becomes that power in the power source. As you might recall from the first course, a photovoltaic is made of a semiconductor material having a negative or N layer and a positive or P layer. When photons or particles of sunlight hit the surface of that semiconductor, electrons within the material gain energy and are put into an excited state. In the case of photovoltaics, excited electrons move from the N layer through the top contacts of the solar cell. Then the electrical energy is sent through the wire to a load where the energy is transferred and the electrons return back to the bottom contact of the photovoltaic. This is a circuit, so the electrons always have to have a complete path. Since this is an electrical circuit as well, we should be able to measure two of the important characteristics, voltage and current, to determine power. But what's the origin of the voltage and the current in a photovoltaic? Well, the voltage in a photovoltaic cell is defined by the size of the band gap, or what we call the energy difference between the N layer and the P layer of that photovoltaic material. For silicon, which is the primary material for all photovoltaics today, it has a defined voltage of 0.5 volts, or about 1/3 the size of a AA battery. Since the voltage is defined by the material and not the size of the material, all silicon photovoltaics will have this voltage, and only by wiring in series can we increase that voltage. Current in a photovoltaic is different, however, and it's related to the amount of sunlight that hits that cell. Well, why is this? More sunlight, or solar energy, means more photons. More photons equates to more electrons being excited. The number of excited electrons that move through the circuit is equal to the current of the cell. It's not, however, equal to the number of photons that initially hit the cell, meaning that not every photon generates a mobile electron. In fact, it's the ratio between electron current and photon energy that gives us the efficiency of our cell. Once electrons are excited, they move through the conductors to the load and dissipate their energy, and then return back to the P side, or back of the solar cell. This is a very simple way of looking at how current flows in a photovoltaic circuit, but it works for this example. In the next segment, we'll look at how voltage and current can be measured within a photovoltaic module and an array.